A very good day, juries. It's my pleasure to present my app called the IntelEye. What is IntelEye? Through IntelEye, we plan to eliminate the use of physical interfaces to communicate with the system, which is the keyboard and the mouse. In this demo app, we've eliminated to a considerable extent actually the use of the advent of mouse and keyboard to communicate with the system. So how are we going to do this? This is done actually by using groundbreaking technology actually, which is called the integrated gaze detection and gesture manipulation technology, which was developed by me, of course, in which we would be interacting with the system with the pupils. The pupil would be taking control of the mouse cursor and assisted by the gaze for clicking, for selecting, etc., and all those things. In this app, this basically consists of two parts, which is the gesture only part and then the pupil detection. Coming to the gesture only part, I use my hands to control the mouse cursor and the other hand to click, scroll, etc. The normal mouse function are replicated by our hands. So let's see how I'm going to do this. So now let's see how the mouse cursor moves. So as I bring my hand onto the in front of the camera, you'll be able to see the mouse move. So let me bring the hand first. This is the gesture for making the mouse move. As you can see, the mouse cursor moves quite fluidically. It's quite interesting notice that we've not done an absolute mapping of the world coordinates onto the screen. This is because mapping absolute coordinates onto the screen is quite tedious and you have to move your hands everywhere. That's not how the mouse and touchpads work. On trying to replicate the functionalities of touchpad, we've treated the air as a touchpad. It's a similar invisible touchpad, and we've bought the same functionality through the gesture. So what is relative mapping? In relative mapping, we take note of each coordinate the hand moves on the 640 and the 320 screen. These coordinates, then the distance is calculated and the timestamp which keeps running provided by the SDK is noted. So we find the speed, which is distance by time, and then we multiply the speed and the distance with the original cursor position on the screen, which is mapped onto the screen. So the original cursor position is multiplied with the speed and the distance, and its corresponding displacement which has to be made is found. So as I bring my hand again, you can see a small displacement I make. The mouse makes a larger displacement on the screen. This is how relative mapping is done. Quite impressive, isn't it? I seriously hope so. So now let's see how we go about selecting apps. I bring my window and I go to K55 and give it a thumbs up. So K55 should open up for me. So inside K55 I have these. Now let's see how I open up all these folders. I move my hand over these things and then I give it a thumbs up if that's the file I want to select. Giving thumbs up, I find application data and then another thumbs up. I'll open bundle software installer and then the other thumbs up. Open it like now. Just in connection, so please try again. So I click. Okay. So now let's open up a different thing. Downloads, for instance. I give it a thumbs up. And there are different things inside downloads. So now let me show you something interesting. I've given a checkbox over here exclusively for Fruit Ninja. So I'm going to show how I'm going to play Fruit Ninja just by weighing my hands over the thin air. So I check Fruit Ninja over here, and then I launch the app. So Fruit Ninja opens. It takes a while to do it, so let's wait. Yeah, here's Fruit Ninja for us. So this is new again. So just by weighing my hands over thin air, I'm able to play Fruit Ninja. This is one of the exciting applications of our integrated gaze detection and gesture manipulation technology. So this is just a sample application of how to play Fruit Ninja in thin air. And that's it. Time's up. So this is how Fruit Ninja can be played using gestures alone, and this is one of the interesting applications of gesture technology which is included in the integrated gaze detection and gesture manipulation technology. Now let me show you an interesting application. I just move my mouse. Fruit Ninja is ticked, if jury doesn't know, and I give a thumbs up. And I can drag wherever I want. So if I want to place it over here, I just deactivate this gesture by closing my thumb, and yeah, it is done. So this is how I drag and drop. The disadvantage of using two hands is anything can get detected as primary or secondary. If your left comes first, it gets detected as the primary, and the right the secondary. So if right-handers can do a power change like this to exchange between primary and secondary. So this is primary now, and this is primary now. So that's how we can interchange between the primary and secondary. So it goes into a lot of confusion at times. If you had seen the video, when I am controlling my mouse cursor using this gesture, sometimes it gets detected as a thumbs up. So I have given the left click functionality as the thumbs up gesture. So at times it gets confused, but still this is a demo app. We can improve on it. This is how gesture works by moving the mouse. This is how we implement the mouse functionalities using gesture and hand movements. So the next feature of IntelEye app would be the type in the air feature. In order to accomplish this, we would be projecting a virtual keyboard, which is nothing but our on-screen keyboard provided by the Windows 8. So in order to activate it, I am showing a 5-finger gesture to activate the on-screen keyboard, and I am making this notepad as the active window so that it enables me to type on it. So I move my hand, and what should we type? It will be H, E, and Y. Hey. So this is how typing is done. On further, basically this evolved as keyboard having two touch inputs, two gesture inputs, but it gave into a lot of confusion. So we decided, as this is a demo app, let us stick on with a single hand and implement this feature. So this is how type in the air feature works, and this function can be applied anywhere, just like the scrolling function, scrolling mouse function, which can be applied anywhere. this can be applied anywhere, wherever you have a text box, and if you show a 5-finger gesture, the on-screen keyboard comes, and then you can type whatever you want by hovering the hand over the keyboard. Now let's move on to pupil detection. The app being named IntelEye had a reason. We believe that whenever we look or see an icon, our pupils focus on the icon first, and then the mouse moves over it to select the icon. So why do we need an external interface to communicate with the computer? Isn't our pupils enough? That this was the main idea behind this pupil detection concept. A lot of people think that whenever we see an icon, our head turns and looks at the icon, but that's a very wrong notion. Actually, even though our head turns, it's the pupil that focuses on the icon. So gaze detection has to be done using the pupils. That is very misunderstood now. So how do we go about detecting the pupil? We've used OpenCV to detect the pupils, combining with the Intel perceptual SDK, which gave us the power to detect the pupils very accurately, and we claim that this pupil detection method is universal. It detects pupils of all human beings in this planet. So now let's go on to the pupil detection. This is done by clicking the checkbox, which is integrated gaze detection and gesture manipulation technology. On clicking the checkbox, we get this pupil detection dialog box. So what it's given there is the specimen which has to be studied should sit comfortably, and we expect that the head of the specimen should not move throughout this calibration process. So what are we going to do is we are now going into the calibration process, which is we make the specimen to look at certain points displayed on the screen. Why do we need this calibration? Because by making the specimen look at different points on the screen, we are able to draw a rectangle. I'm able to draw a rectangle, and then through this rectangle, the pupils are absolutely mapped to the screen coordinates. This is why we need the calibration, and this calibration is session oriented. So if a person sits for one session, he has to stay in that position throughout the session, and if he changes the position, the calibration has to be done again. So now let's start with the calibration. Please stare at the blue point, focus on that point alone, shown on the middle of the screen in the upcoming window. So now the specimen looks at the center point, and the values are noted down. And if you notice closely, the values differ by only 1 pixel. If the values differ only by 1 pixel, it is then termed accurate. If it differs by a definite value, it is wrong, and the calibration has to be done again. Now we go into the second stage of the calibration, which is looking at the bottom right of the screen. So now the specimen looks at the bottom right of the screen, and the coordinates are obtained. Here too, the pixel difference should be only by 1 pixel. And then we go on to the third mode of calibration, which is looking at the top left of the screen. After that, the calibration is over, and now we are going to detect the pupils as accurate as possible. Now if you notice, as my friend moves his eyes over the screen, you can see the arrow marks getting highlighted by the round which is drawn over the arrow mark. As he sees the corner of the screen correctly, the arrow mark moves correspondingly, following his gaze. So this is how we do this gaze detection, and it is very accurate. It is so very accurate that if even if he changes his head position and if he moves his head towards the right corner of the screen, the arrow mark moves to the right corner of the screen, and if it's the left corner of the screen, the arrow mark immediately moves to the left corner of the screen. This is how the pupil is exactly mapped, and it is accurately tracked. This is all about the integrated gaze detection and gesture manipulation technology. This is done by obtaining an image, an eye image, which is then run into a correlation function, which maps the specimen's eye image with the given input image, and then the matching portions are taken and the pupil is correctly detected. So in this pupil detection algorithm, what we do is normally your eyes moves if throughout the pupil movement is about 40 pixels horizontally and only 8 pixels vertically, which is very small when you compare it with the resolution of a screen, which is 1366 into 720 usually. So what we do is we split this rectangular window into grids, 40:8 grids, and we plot the intersection points. We map the eye pixels with those intersection points, and that is one of the reasons for the mouse movement appearing very jittery. This can however be overcome by slowing the processing speed, so that we can draw a straight line between the two pixels. So in this demo app, we've detected the gaze direction correctly. What I would say is, with the given resources and the given time constraint, we're able to detect the pupils correctly and find its gaze direction. So the gaze point will be the holy grail of the IntelEye app, because gaze point is the accurate point at which the point of intersection of your two eye pupils, which will be the actual point of incidence on the screen. So we're just 2 steps behind of finding the correct gaze point. With still a few more research and few more resources, we would be able to detect the gaze point correctly and make this IntelEye app a reality. This is IntelEye, and I'm Karthik signing off. Thank you, juries. This is Karthik on behalf of Impactt Technologies.